Welcome. Thank you for joining us. My name is Ismael Lemhadri and I am a PhD student at Stanford University. Today, I will be presenting our work called LassoNet, a neural network with feature selection. Perhaps the most important slide of all is this one, to acknowledge that this is joint work with Fangru Wan, who is a postdoc scholar at UC Berkeley and my advisor at Stanford University, Rob Tipshuran. And by way of an introduction, I am putting a slide here about modern machine learning and how we're dealing with larger and larger models with massive amounts of data. And over the last few years, this computer vision competition has witnessed the dramatic improvements in the power of these machine learning tools. In just 2010, 10 years ago, the best performing model had an error about 27%. And the techniques that these models used were quite traditional compared to what you might witness today. They relied on ideas on heavy feature engineering and ideas borrowed from support vector machine literature. And over the last years, we've witnessed a systematic trend where the best performer is a neural network-based model. This has been consistently the case, and this continues to be the case until today. So with this trend becoming ever more prevalent, and as we've seen, and as we continue to see the many applications of deep learning throughout the entire spectrum of industrial problems, be it gene sequencing, advertisement, and speech recognition, essentially whenever you have a data-rich problem, I still would like to actually go back to a very old yet fundamental problem that has a strong relevance, say, in biology, where you have a structured data set where you can measure, say, genomic features for patients or individuals. And these can be, there can be many of these features, but on the other hand, you have a certain response, that's, say, a binary response, which is the presence or absence of a disease. This is a fairly different setting from the one I presented in the previous slides, because the data is more structured and the features have a clear meaning. Another big difference is that in these kind of problems, the shape of the data is usually such that there is a lot more features than individuals. So there's quite a few differences, and the focus on our talk will be on this kind of setting. In these situations, it is the case that much of the information in the features is irrelevant for predicting the responses, and only a small subset is informative. And feature selection methods provide insight into the relationship between features and an outcome, while simultaneously reducing the computational expense of downstream learning by removing features that are redundant or noisy. It is needless to say that with high-dimensional data sets becoming ever more prevalent, feature selection has seen widespread usage across a variety of real-world tasks, including disease detection. This is an example based on protein data that shows some of the benefits of feature selection. And considering the cost of protein measurements, a trade-off between the number of features kept and statistical performance is often very desirable. In this example, the number of features kept by our method is shown over an entire path, and the statistical performance corresponding to each number of selected features is shown on the y-axis. So in this example, the method captures 70% of the signal with about 20% of the features. Therefore, this allows to narrow down the list of important features and therefore makes the conclusions of the prediction task more actionable. And it also has an important result from a biological perspective, as this can help understand the scientific problem and provide an understanding for downstream learning. In terms of existing work on this domain, the literature is extremely vast, but feature selection methods can generally be divided into three groups: filter, wrapper, and embedded methods. Without going into the details about these methods, I will just say that embedded methods are the most appropriate when you have an outcome of interest, so that you learn features in a supervised way and therefore combine feature selection and learning. And a well-known example is the lasso, introduced by Rob Tibshirani in 1996, which can be used to select features for regression by varying the strength of L1 regularization. However, one of the limitations of lasso is that it only applies to linear models. And recently there has been a great interest in extending this method and generalizing it so that it can capture arbitrary kinds of nonlinearity. And this is the regime where our method fits. By way of an appetizer, this is the results using our method, LassoNet, to simultaneously select informative pixels and classify digits from the MNIST dataset. And the classification accuracy is shown again by number of selected features. The formulation of our method relies on a hierarchy principle. This is meant to provide a regularization where the problem is where the data is complex and neural networks do not have any guiding principle, which might not be such a great setting for the data and the problem setting I introduced, where the features are structured and meaningful. We provide a natural hierarchy principle that has been used in the past and that allows to tie together the feature selection and the neural network. Our approach is specifically based on residual neural networks, and the formulation of the method I will show in a few slides, but first, this is the architecture of the method that relies on an arbitrary architecture. It can actually be implemented by adding just a few lines of code to a standard neural network, and on top of that, a residual layer that preserves a linear component and that gives the linear part of the signal prominence while also allowing to capture nonlinearity. The objective function here budgets the total amount of nonlinearity involving each feature according to the relative effect importance of that feature as a linear variable. In this objective function, the loss is shown together with an L1 norm only applied to the residual linear collection. And in this framework, feature sparsity becomes possible with a controllable trade-off between the linear and nonlinear components of the model. This involves a few hyperparameters. The first one is here to encourage sparsity and to perform feature selection. And the second one is here to budget nonlinearity and acts as an added regularization. So this formulation has several benefits. First, by promoting the linear components of the signal, it uses a well-known hierarchy principle that has been extensively studied in statistics and that has several regularization benefits. In addition, the formulation leverages the expressive power of residual neural networks that have been shown to be easier to train and, of course, can uniformly approximate any measurable function. And by tying every feature to a single coefficient, which is the linear component, this formulation provides a natural framework for feature selection. The training loop for LassoNet is shown in this algorithm, and it looks like a regular standard algorithm for doing gradient descent and then learning the parameters. So I will just show you the feature selection path for when you apply the method on mice protein dataset, and then you might notice here that there is a path. So how do we get such a path? Well, I will emphasize the nature of the regularization here that goes over a path from dense to sparse by increasing iteratively the value of the penalty lambda, and then applies a dedicated hierarchical proximal operator in order to perform the feature selection. We have noticed that it is very important to train from dense to sparse rather than sparse to dense. And this allows to actually effectively leverage the good local minimum that was fine for the dense model that was completely unconstrained, and then use that over the entire path using warm starts to preserve the good generalization properties of this dense local minima throughout the sparse path. This effectively amounts to pruning, and it turns out that the model is separable over the features. This framework is actually extremely straightforward to implement in standard deep learning frameworks, and the computational complexity is only a minor overhead compared to the cost of computing the gradients, which is commonplace in any deep learning algorithm. I will conclude with an experimental evaluation. In this final section, we show experimental results on a real-world dataset. These datasets are drawn from several domains, and there is more information in the paper about the datasets, but basically what we do is we compare LassoNet with several supervised feature selection methods that are considered state-of-the-art. In these experiments, we benchmark the feature selection methods with varying number of features. Although LassoNet is an integrated procedure that simultaneously performs feature selection and learning, most other feature selection methods are not. These methods do not exploit the features directly into the learning problem, but rather they must make use of the selected feature set as input to a separate downstream learner. And therefore, we run each algorithm being evaluated on the selected features using a downstream learner here that consists of an extremely randomized tree classifier. The results are, which is a benchmark, that's a method that is being used for feature selection in the past, for testing feature selection methods in the past. The classification errors are shown in this table. And overall, we find that our method is the strongest performer in the large majority of classes. And there is more results, again, in this table. And occasionally, more than one method achieves the best accuracy, but we find that our method either ties or overtakes the remaining methods in all instances. And this suggests that the hierarchical objective may be widely applicable for different learning tasks. As a summary, I have presented a neural network-based model that allows to perform feature selection. In this presentation, we have shown that unlike most other feature selection methods, our method is data-driven and provides a path of regularized models at a cost that is essentially that of training a single model. The method uses proximal gradient descent and leverages the stochasticity of the initial dense model in order to efficiently explore and then converge over an entire regularization path with varying number of input features. This makes LassoNet different from many feature selection methods which assume prior knowledge of the number of features to select. There are several ways of extending the method beyond supervised learning. In fact, in several other applications, the specific prediction task may not be known ahead of time, and therefore it is important to develop methods that can identify a subset of features while allowing imputation of the remaining features for arbitrary downstream tasks. This is an unsupervised approach, and it adapts very simply to our model by simply changing the last layer of the network. There are several other possible applications to this method. For example, by providing deep neural models for survival times. Another potential application is to matrix completion problems. These problems are explored in more detail in the paper. Thank you for joining our talk today. We have also made a poster that will be available at the Bernoulli IMS Symposium. I would like to thank my co-authors as well as Louis Abraham for help with the implementation. And we have made all the resources for this talk available on the internet in order to reproduce all the results.